So hi all, in this video I'm going to explain DFA, NFA and epsilon NFA. Epsilon NFA means the epsilon transitions and how the epsilon closures are taken. Uh, First, I would like to say what is DFA, deterministic function automata. So in this, I'm just conveying the basic and simple topic in simple manner. So not much deep I'm not going in. So if anyone needs any references, you can check any relevant publications regarding to it. So in DFA, there's only one deterministic path. So in this example, I am just writing this example for getting the concept very clear for you guys. So it may not be appropriate, or maybe some issues will be there with these examples. So try to get the idea only and elaborate it with according to your thoughts. So in DFA, there will be only one state, one transition from a state to another. So here the states are numbered. 1, 2, 3 are the states. A, B are the alphabets. So from state 1 to 2, using the alphabet A, when the alphabet input is A, the transition occurs. So from state 1 to state 2, when input is A, alphabet A, it will transfer or transition occurs from 1 to 2. So in DFA, there will be only one type of transition in it, and in NFA we can see that there will be more than one transition. That's why it's non-deterministic finite automata. There can be more than one transition from a state to another, so there won't be any single transitions mainly. There's chance it can be single also, but here in this example I'm showing that from state 1 to 2 and 1 to 3 it can transfer according to the inputs received, which can be A and B. So if in this it is a NFA, so it can move more than one states normally. So basically in the epsilon transitions for an NFA, the epsilon symbol is used. You can use a E shape or sigma shape, it can be anything. The epsilon transitions are shown here. I'm using a scanned PDF, so try to understand the concepts. From the state 1 to 2, there's an epsilon transition, and 2 to 3, there is also an epsilon transition. It means that there is no input alphabet is taken. Epsilon is not considered as an alphabet, or it is simply saying, for getting the concept clear, we can just say that it is a nil or null value. So 1 to 2 can transfer transition occurs without even a alphabet is taken as input. When comes to epsilon closures, where the path of epsilon moves, that is the closure taking. So in this example, if we take the state 1 and it has an epsilon transition, we can add that 1 to its closure set. We make a set out of this example. So in this example, if we take this set from in the set 1, which is of state 1, from state 1 to 2, there is an epsilon transition. So we can move from 1 to 2 using epsilon transition. So the state 2 is also added. Generally, while starting a state, if it is state 1 or state A, state B, anything, we will just add that particular starting state to the closure set. So that's why the 1 is here. Then the second state is reached from 1 using epsilon transition, and from 2 to 3 there is also epsilon transition. So 2 and 3 are also in the set. So the same goes for the state 2. So while we are doing an epsilon closure, we will take closure for all the states present in a particular NFA. It is done in epsilon transition of NFA. So all states of NFAs are taken. In this example, there are 3 states, mainly 1, 2, 3. Normally in NFA, we won't show the final state. Here we can say that 3 is the final state. Normally in DFA cases, as you seen in the above example, the third state is marked circled twice, which means it's the final state. Normally in an FA we won't do that. Now coming back to the point, taking closure for 2 and 3, stage 2 and 3. In stage 2, starting at the point also, we are including stage 2 itself to the closure. From 2 to 3 there is a epsilon closure, that's why we are taking it. And 3 also, as I stated earlier, if you are taking the particular state, we will add that particular state to the closure itself. That is 3 is taken into it. And in here we can see that epsilon closure is also present in 3. That is, even if we didn't get any input from state 3, it will loop in the state 3 itself. Normally we can avoid epsilon also. I'm just showing it as an example in that. So this epsilon NFA won't be a complete or a perfect one. So guys, coming to the next example, it's a complicated one. Actually, not a complicated one. It's simple. We have to find the epsilon closures in this particular NFA. In this particular example, we have four states: 0, 1, 2, and 3. So wherever a path that is moving according to the epsilon transition, we take its closure. For all states, we are writing down the closures. For state 0, if we look at the epsilon transitions, 0 to 1, there is an epsilon closure. So at first, starting itself, 0 is added to the set. Now 1 is in the set. From 1 to 3, there is an epsilon closure. And from the 3 to any other point, there is no transitions using epsilon. So 0, 1, 3 is in the set epsilon closure set of 0. In this manner, we are doing it for state 1, 2, and 3. So from state 1, we can see that the transition is only to state 3. So 1 and 3 are in closure set of 1. But that's a little change. Reverse is happening for state 2. So when we take state 2 is added to the closure set. And when we look there, we can see that state 2 has epsilon transition to 1. So normally when we consider state 2 as transition to state 1, so after state 2 is included in the set, we will add state 1, and from 1 to 3 there is also an epsilon transition, so 3 can be also added. And also there is another transition 2 to 3, there is a direct epsilon transition, so already state 3 is in the closure set, so we don't need to add 3 again. And from state 3 itself there are epsilon transitions, so it is also in the set. So this is all about the epsilon closure, how to find epsilon closure, and what about the epsilon transition. If you have any queries, you can comment it, or you can refer the publications related to it.